Okay, we're back with some more about the Pythagorean Theorem. If we recall, the Pythagorean Theorem says that a squared plus b squared equals c squared, and here we have images. So I'm not going to call this a proof because it lacks rigor in every sense of the word, but it is a neat illustration and it can be used conceptually to prove the Pythagorean Theorem. In fact, it's one of the earliest proofs around. So some of that lack of rigor is you're going to just have to take me at my word that these two figures are indeed squares and they are congruent. This figure is our triangle and is labeled as a right triangle, as noted by the right angle notation there. And we have the sides labeled A, B, and C, which correspond to A squared, B squared, and C squared. C, of course, being the hypotenuse. And these chunks of paper over here are all representations of the squares of those sides. So this one was a square when it started. Again, you're going to just have to trust me on that. I cut it into pieces for a very important reason that will be very clear when we start assembling everything. But for now, we'll take A and its square. So we have the A squared portion of our Pythagorean theorem represented by these 5 pieces of yellow paper that I promise started as one yellow square. And then we have this one piece of paper that is a square with each side equal to the length of b. And then we have our other piece, which is a square of the sides equal to the length of c. So we have squares based off of our sides, and again, we're looking at a squared plus b squared equals c squared, so the Pythagorean theorem claims that the area of this square plus the area of this square is equal to the area of this square. Now we'll take our squares and put them up into our empty squares, and the hypotenuse gets its own, so it fills that square completely. And now we'll take b squared and move it up, and then this is why we had to cut a squared into pieces, because obviously I can't fit a square based off the side length of a anywhere on here. But if I cut up that area, the area remains the same, and I can get these two guys to go up here, and then these 3 littler squares will round the corner. Incidentally, rounding the corner is a terrible geometric statement. Corners are not round and rounds are not corners. But you can see that it illustrates that a squared plus b squared equals c squared. Again, I'm not calling this a proof. There's no rigor here. It's just a neat illustration, and theoretically it can be proved. But there are problems with precision of doing a physical model like this. Obviously my lines have width. Lines in geometry do not have width. I am not physically capable of creating exactly congruent squares, and I'm not physically capable of cutting out congruent squares even if I were capable of drawing them. So this is an illustration, kind of a hand-wavy proof, if you will, of the Pythagorean theorem. Thank you.